Welcome to this NPTEL course on Advanced Pre-Stress Concrete Design. We are in the module 10. We are in the part 3. In this part of the module, we are going to talk about equivalent frame method for analyzing the post-tension two-way slabs. What are the expected learning outcomes? After the student goes through this video, he or she will be able to understand the concept of equivalent frame for PT slabs and gain knowledge on the analysis of slabs using equivalent frame method, particularly on how to discretize the slabs and what are the steps involved in equivalent frame method analysis and determining the flexural capacity, what are the procedure, and understand the shear design considerations for post-tension slabs. Okay. So, as the name suggests, we are going to convert the slab system, two-way slab system into an equivalent frame. So, what we are going to do is, we are going to take a typical floor slab and then create a equivalent frame, and we are going to analyze it like a two-dimensional frame. So, it is a structural analysis approach developed to estimate the moments and forces in two-way slab systems in general, because here we are talking about post-tension slabs. So, this method can be used for analyzing the post-tension slabs as well. Well, in this method, what we are actually doing is structural analysis. So, we are doing elastic analysis of an equivalent two-dimensional frame, and that composes of slab strips, and the column which are above the slab and below the slab are assumed to be fixed. So, we also include the columns above and below, and in addition to that, we will also include any transverse beams if there are there also as part of the equivalent frame. Now, this method is used for analyzing the two-way post-tension slab for service conditions as well as for ultimate conditions, right. So, we can do the for both checks for service condition as well as for ultimate condition. Now, this is a slab that if you look at it here, so what I have done is, if you look at it here, these are different column lines that you have that runs from, let us say, north to south direction, and then you have a column line here also, it runs along east to west direction. So, what we are going to create is a frame like what it is highlighted here. For example, this will be a frame in the east west direction. We take a typical frame. In fact, we take one interior frame and one edge frame, and then we do the design, right. So, for example, if I consider this is a plan view of a PT slab, and you see this, you have different structural arrangements that are given here, right. For example, when I look at a section along this line, let us say AA, then what you see here is, if I take the sectional elevation, what you see here, this is your slab, and the slab at a different column supports have different configurations. For example, here you have a capital, column capital. Here I have a drop panel and a capital. In this last span, when you look at it here, the slab also has a beam, right. In addition to that, you also have a transverse beam which is running perpendicular to the direction where we are doing the analysis. So, you see here, the slab can have different boundary conditions along the length of its frame, right. In addition to that, it can also have some members that are connected in the transverse direction. So, the equivalent frame method is quite helpful in analyzing even this different boundary conditions, whereas another method is called direct design method, which we cannot use when you have this kind of complex configurations of a post-tension slab. And that is the reason equivalent frame method is widely used, though nowadays the design engineers, they use commercial software packages for doing the analysis, but it is always prudent to check the results using some simple Excel sheets that can be developed on the basis of equivalent frame method to verify whether your software analysis results are making sense or not. So, that is the reason of including this very important chapter, because post tensioning is very commonly used for creating slab systems, and it is highly economical as we have discussed in the previous parts, but however, the analysis results have to be checked thoroughly, right. So, what we are doing here is the slab is divided into series of two-dimensional frames in each direction, like I said, north, south and east, west. And then what we are doing is, by moment distribution method, we are trying to get the positive and negative moments using some elastic frame analysis. Typically, moment distribution method is what we use, right. And this method is actually satisfactory for symmetrical and those with unusual dimensions or loading. Even if you do not have different types of loading, again we know that moment distribution method can be quite easily used for different geometries and different loading conditions, right. So, this is a big advantage with your post tension slab system analysis using equivalent frame method. Okay, now, this is an example. For example, if you see here, this is a slab that you have, a PT slab. Now, if you see, the columns are all not at straight. So, you have like this, then you have like this, then you have like this, and you have like this. Similarly, in the x direction, you see it goes from here to here, here, here. So, the column lines are, depending upon the architectural requirements, the column lines are typically, they are not straight and they will have some offsets. So, that is the reason we cannot use other simplified methods like direct design method if you have unusual geometries where your column lines are not actually straight, right. So, as we have discussed, this slab, if you take it, we are going to divide this into series of two-dimensional frames in each direction, and we are going to calculate the positive and negative moments using elastic frame analysis, right. Now, how do we do that? For example, this is what I said. We are going to divide the slab into frames along each column line with some assumptions and approximations, right. And for example, this is an edge frame, and this is an interior frame, right. So, if all the interior frames have nearly same geometry, then you can do only one interior frame and use the same design for the other frames. So, but if your geometry and loadings are different, then you have to create this equivalent frame along different column lines with a different geometry and loading, and you do separate moment distribution method of analysis, right. Similarly, if you look at it in the east west direction, so like this we create frames, right. So, and we do the analysis in the two orthogonal directions, right. Now, each design strip is extracted and idealized in isolation, right. For example, if you look at it here, if I look at for a G plus 2 kind of structure, this is how the frame typical section looks like, but we are not going to analyze all three of them at once. For example, if I look at this one typical PT slab and then I design that, if my column dimensions, if you do not have any floating column and column alignments are nearly same, then the same design can be used for the other typical floors. So, that is the idea, right. So, we are here, we can see that you are doing only the frame analysis, and whatever the reinforcement that you get as per your moment distribution that you have along the frame, that has to be distributed along the orthogonal direction according to the width of the strip that you have. Okay. Now, this is what we said. Typically, we are going to the frame, again we are going to divide the slab into series of design strips in two perpendicular directions of the structure. And why do we do that? For example, let us say even if I take one particular frame, right. So, you see here, this is for example, let us say this is the typical one particular frame that I am doing, right. So, I will have a middle column strip. Typically, column strip regions will be stiffer, right, and then you will have half of your middle strip like this highlighted region. On either side, you will have middle strip. So, we divide it. So, this is basically half of middle strip, right, and this is again another half. The reason why we do that here is, in the last lecture also we have discussed, if I can put more PT cables and more reinforcements in the column strip region, that helps me in achieving a very nice load balancing. So, very nice uniform distribution of load balancing can be achieved. So, that is the reason we said the recommended is typically from 60 to 80%, and it is very commonly used is 75% of the reinforcement, PT reinforcement is provided in the column strip, and the remaining 25% is provided in the middle strip. Okay, this is a generic guideline. Of course, it can be changed depending upon the layout what we have. Now, for the strip, that is the frame that you are doing along the direction, typically the spans are considered as L1, and the perpendicular width is typically taken as L2. Right. So, for example, this is an interior strip and this is an exterior design strip. Now, what is a load transfer system? We will talk about. In the equivalent frame, I am going to have a slab beam member which will be along the span we are doing the analysis. The span is, as we have discussed, it is going to be L1, and in the orthogonal direction the width of the strip will be taken as L2. Right. And it will also have columns or walls, other supporting elements that are connecting to the slab. In addition to that, there may be beams which are running perpendicular to the frame. So, those are called as torsional members, which are transfers to the frame, which are along the span L2 and along the column lines. These are the three important components that you will have in the load transfer system in an equivalent frame. And this is a picture. For example, if I am doing the analysis on this particular design strip, then you can see that you have a column, sorry, you have a slab, and then you have this member ABC is actually a member beam that is running perpendicular to the span where we are doing, that will be contributing in torsion. So, we have to account for that, right. So, that the torsion stiffness of that member has to be included somehow in our equivalent frame, right. Then you have a slab, and then sometimes you may also have a beam, below that you may also have a beam, right. So, that is why it is called a slab beam member. In a typical flat plate, you will only have slab, and if you have a flat drop panel also may be there, right. If you have a flat slab, you may also have a drop panel or with capital, but in a typical flat plate or a flat slab, you do not have the beam that is running along the span direction, right. So, but you may have, in a generic case, you may have a beam as well. So, that is the reason this element is called as slab beam member, right. So, then what we do is, each design strip is extracted and idealized in isolation. These are the steps that are involved in equivalent frame method. Then what we do is, this is one particular story that I am taking, and I am going to assume the story below and story above columns as fixed, which is a reasonably a good assumption, right. Because relatively, if you see, they will act like a fixed support. And I am going to take one floor of a multiple story frame, and then I am going to do the analysis, right. And the ACE code allows a separate analysis of each floor with the far ends of the columns considered as fixed, which is reasonably a very good assumption. And this is a typical substitute frame, right. Now, this substitute frame, what I can do is, I can convert into a single equivalent story, right. So, this is, this you have, because I have column above and column below, that can be converted into a single column, okay. That typically, we idealize this as an equivalent stiffness like this. In addition to that, if we have a beam that is running perpendicular to the frame, that beam also will act in torsion, because if this frame is rotating like this perpendicular member will be subjected to twist that we have studied in the torsion chapter, right. So, that torsion stiffness of this orthogonal member also has to be included in somehow in the stiffness of the members. Usually what we do is, we club the column above and column below and the torsional beam as one thing, which is called as an equivalent column. So, that is what we write here, which is an equivalent column. So, we club this column above and column below along with this torsional beam and call that, find the equivalent stiffness, and we model that as a single story frame. So, let us now look at the individual elements. For example, in a slab beam element, we know that for a prismatic member, when we do moment distribution method of analysis, if your cross section is not going to change, you know your stiffness factor is taken as 4 EI by L is the stiffness of the member, right, and the carryover factor is taken as 0.5. And also for a fixed end moment, because in moment distribution method, as you know, we are trying to lock the joint and unlock the joint until the equilibrium condition is achieved, right. So, when you lock it, you arrest the rotation, so your fixed end moment will develop, which is going to be equal to WL square by 12, right. So, which is actually 0.833 WL square. Now, in our case, depending upon the boundary conditions of the column, for example, column may have a drop panel, capital. So, you may have a varying stiffness along the length of the column, right. So, for a member that is stiffer at the column slab joint region, typically the flexural rigidity, we call this EI, which is a flexural rigidity, is greater, and the slabs with drop panels and column capitals will be stiffer near the column, right. So, the slabs with the drop panel and the column capital, as you know, it is going to have a higher width and higher dimensions. Obviously, at those regions your flexural stiffness is going to be high. So, the equivalent frame method takes the variations of these stiffnesses into account for these slabs or slab beam element. Then we know that the stiffness factor will be greater than 4, because you do not have a prismatic section anymore, you have higher stiffnesses along the length of the member. So, it will lead to higher stiffness value, typically it will be greater than 4, and similarly the carryover factor also will be greater than 0.5, and also the fixed end moment will be also be higher than WL square by 12. Now, all these values can be found for different configurations. People have already done using column analogy method, people have derived for with certain assumptions on the boundary conditions. The values are actually tabulated and it is readily available, and that can be used to create your stiffness properties and carryover factors for doing the moment distribution method, right. Okay. So, this is what we said. Professor Hardy-Cross was the first one to use the column analogy method to develop this stiffness factor, carryover factor and fixed end moment. So, for PT slabs or flat slabs and flat plates, readily there are tables available depending upon the boundary condition that you have. These coefficients can be taken directly from the table. Okay. Now, just to explain why this slab beam stiffness will be varying. For example, if you see here, we are looking at a slab panel element which is flat plate. For example, this is a flat slab, right. So, depending upon where I am taking the section, my dimensions are going to change, right. So, and you know the moment of inertia is BH cube by 12, right. I typically for rectangular section we take like that, depending upon where I am taking the section. So, if I am taking at the section AA, my moment of inertia will be I1, which will be, if I take 1 meter strip, B1, which is 1 meter, and then H is the thickness of the slab, BH cube by 12, right. So, this is one moment of inertia. But if I take the section right here where the drop is there, now you see that the depth of the slab is the depth of the slab plus the thickness of the drop. So, my H has gone up. So, my moment of inertia will go up. So, that is the reason you see here my moment of inertia has increased in this region wherever you have drop panel. Now, the same thing if I am taking a section which is also including the column capital, and then you will find that you will still have higher depth, you can maybe take an average depth, and then you will find that the moment of inertia is going to further increase. So, what we are trying to tell here is, because of the change in geometry along the length of the slab beam member, your moment of inertia is going to change along the length of the span. So, that also has to be taken into account, and typically in a typical moment distribution method we do prismatic members, but here it is not really valid because your moment of inertia is changing along the length of the span. In addition to that, if you also look at the column, if I take the column here, I will have one moment of inertia. If I take here, I will have one moment of inertia. Now, if you take a section for the column, Now it is all stiffened by the slab, so your moment of inertia will tend to become very high, which is infinity, right. So this is the variation of moment of inertia for the column as well. So there is a moment of inertia variation for the slab beam element, there is a moment of inertia variation for the column element. Now these are the different sections that we have discussed, A, B, B and I2. So then section CC, we try to get this as I2 by 1 minus C2 by L2 the whole square, right. And then the variations of the column stiffness also we have briefly discussed. This is for a case for slab system without any beams. You see here flat plate structure. Even for a flat plate structure, the column at this sections you will have EI flexural stiffness, but if I go to this region where it is also having slab, then your moment of inertia will become high because your breadth is going to be very high, right. So that is the section, because I have to take a larger width in my calculations. This is the column stiffness variation. Similarly, for a slab system with the drop panels, you find that again you have this kind of a variation for the column stiffness. Again, for a slab system with a drop panel and capital, you are going to have variations like this. It goes like this and comes, right, and you get this kind of variations in your column stiffness. You can also have a beam like this, right. Then also you can see along the beam dimension your moment of inertia becomes close to very high value, and then here you have EI. So there is a variations in the stiffness along the length of the column. There is also variations in stiffness along the slab beam element. Now what is the equivalent column, right. So we looked at first we looked at slab element, we looked at the column. Now how do we form an equivalent column? I have explained the typical substituted frame has to be converted into a single story frame. In the single story frame, you will have only slab beam element and the equivalent column. The equivalent column will consist of columns above and below the slab, and also any member that is attached and which is running in the perpendicular direction, which is on the both sides of the column. Now the stiffness of the equivalent column is typically taken as KEC, and you see here when I apply this joint, it is going to rotate like this because it is assumed to be a rigid joint, right. You will have rotations, the joint will rotate by the same magnitude. Now if you look at this, consider this beam and column frame that what we have. If I know the stiffnesses of both the members, this and this, beam and column, then I can find out what is the joint rotation, right, for any applied load. So that is what we do, right. So we can do that. But in this case, in an equivalent column member, now I may also have a beam that is running perpendicular to direction. Now when this joint is rotating, right, it will also undergo twisting for the member that are connected, which is running perpendicular to its direction, right. So but however, the twisting will not be uniform, and you will find that the stiffness where the beam is connecting close to the column will be high. As we move away from the column region, the stiffness will be less, or in other words, the rotation far away from the column region is going to be higher compared to what we have. For example, theta A and theta C here will be higher than what you have for theta B at the joint B, right. So the rotation theta B is the column beam joint. The rotation theta A and theta C are the end of the torsional beam, are typically greater than theta B because of the flexibility in the torsional beam, right. So as a result, average rotation along the edge of the slab, which is line ABC, will be greater than the rotation at the joint, right. So we have to include that average rotation using flexibility concepts, right. Now let us see, the concept of again equivalent column is mainly introduced to account for increased flexibility, that is what I said, because the flexural restraint will be reduced somewhat of the correction of the slab beam member to its support. Now the slab beam is connected to the column, and for most of the widths it is only through torsional member, right, because the slab beam, when you look at it, the connection to the column, the slab beam width, when you talk about it, can be about 7 meters, 8 meters depending upon the geometry of the panel, and the column dimensions will be typically 400, 500 or 600 millimeter by 600. So the slab beam is connected to column only over a small width, but for the entire perpendicular direction, it is connected only to the beam if at all you have any. In a flat plate, you will not have that, but it will be connected only to the column. But if you have a two-way slab with beams, then the orthogonal beam will be the one that will be supporting that slab beam for most of its orthogonal direction. So, we have to calculate this equivalent stiffness using this flexibility principles. Now, I have two columns that are connecting to the top and bottom. So, that is pretty easy. So, I can sum their stiffnesses. Now, the orthogonal beam is going to contribute to torsion, because whatever the rotation that is happening, that will be the twisting for the orthogonal beam. So, the torsion stiffness have to be included. So, in this way, I can calculate my equivalent stiffness like this. So, this is the expression for equivalent stiffness. So, here finding the stiffness of the column member is quite easy, because typically they are prismatic members, and the torsion stiffness of the member has to be included, right. So, let us look at it now. The torsion stiffness is calculated using this formula, which is 9E into C into L2 into 1 minus C2 by L2 the whole cube. It depends upon again also the width of the column to the width of your perpendicular direction L2. L2 is the span which is perpendicular to the design strip or the width of the design strip. So, depending upon how much it is supported, again the torsion stiffness will change. And C is a property which is a torsional stiffness constant, something similar to your moment of inertia, right, for torsion. So, E is your elastic modulus of the concrete, and C is the torsional property of the section that we have discussed, and C2 is the width of the equivalent rectangular column, capital or a bracket. If you have a capital or bracket, we convert it into an equivalent width, and then that is measured transverse to the direction in which the moments are being. So, that means it is not along the span, it is perpendicular or transverse to the span where we are doing the calculation, right. So, now again we have said the stiffness of the equivalent column, again the principle is for a particular moment we have to use the average rotation of the edge beam. So, you know that the inverse of the stiffness is called the flexibility, and which will be equal to the average rotation of the joint between the edge beams. So, the average rotation is basically the theta, the rotation that is happening in the column joint plus the theta beam of the twist. Now, I have to use this for calculating the equivalent column stiffness. So, that is what we say. So, this is the stiffness of the column, and this is the beam twist rotation that it is happening. So, this will be your equivalent rotation of the equivalent column. Now, how do you find your torsional constant? It is a sectional property. So, what we do here is if you have, for example, T beam or an L beam, then I have to divide this beam into rectangles and I have to sum them up to get my C value. So, simplest procedure is the way we divide it should be in such a way that the C value should be high. So, I have to divide these L section or a T section into number of rectangles. The rectangles have to be divided in such a way that it produces the highest value of your C value, right. For example, you see here this L section, we have considered x1, y1, this is x2 and y2, right. So, typically, to avoid, so you have to make sure that the lowest between this x1 and x2, let us say x1 is smaller, that x1 should have a longer y. So, that is the way that we need to do it. In this case, for example, let us say if x2 in this case is smaller than x1, that is the reason the y2 is having longer than y1. So, in that way, if you select it, automatically you will get your higher torsional stiffness parameter, where x is the shorter overall dimension of the rectangular part of cross section and y is the longer overall dimension of the rectangular part. So, these are all definitions for x and y. The cross section is again divided into separate rectangular parts, and then we sum in such a way to give the largest value of C as shown in the figure, right. So, now you understood that we have created an equivalent column, single story frame. Now, of course, I have to find the stiffness parameters that I will be using the tables that are developed for different boundary conditions, right. Now, what are the steps? Let us assume that I have come up with the thickness and I have come up with the PT layout using some first principles, right. Now, I need to find, because this is a statically indeterminate system, while you are doing pre-stressing itself, you will develop some restraint moments. That also has to be considered, right. So, for different design strips, again I said we are doing equivalent frame method for different strips, right. We have to first determine the fixed end moments due to final pre-stressing after all the losses. Of course, the losses also have to be accounted, right. Post tensioning, we have seen that friction losses can be quite significant, and you may also have elastic shortening, because typically when you have a bonded or an unbonded system, you have more cables, so you cannot stress all of them at once. So you try to do the stressing in a sequential fashion. So in a post tension system, when you do the stressing in a sequential fashion, of course you will have the losses, but we have discussed how to calculate the losses, so that can be done. Then what we do, we analyze the equivalent frame method for mainly to find the restrained moments from pre-stressing, because when I want to design for capacity, right. So from we have to include the hyperstatic moments, as we have discussed in the previous part of the model. Hyperstatic moments are the moments that are created because of the virtue of the restraints that you have in the system, right. So these restraint moments have to be first calculated. This is your step 1. Of course, in the next week module, we are going to go through one detailed example how to do a post tension flat plate. Then you will know how to calculate these moments, and we will also, I told you, we are also going to compare these results with what the commercial software package is going to produce. That we will discuss it in the next module. The first step is anyway to include the effect of pre-stressing and then find what kind of restraint moments are produced. So that has to be taken into account, right. Then we are going to analyze the frame for the effect of dead and live loads. These are your superimposed loads, so all of them have to be done. So you have to do the frame analysis also for multiple things, then you can apply your load factors, and then you can use your superposition to find your final moments. So you can calculate the final moments using appropriate load factors by superposition, right. So you get moment from here, restraint moments, M restraint, let us say, and these are your demand. Then with the load factors, let us say typically 1 and 1. So if you have different load factors, then you have to do only dead load and then only live load. You have to do it multiple times, but once you have an Excel sheet, so it's very straightforward to run the numbers, plug in the numbers and get the numbers. So then you add your load factors and then add them up, because we are doing elastic analysis, so superposition is valid. Then finally you get your final moments, right. So then the final design moments are used for checking stresses in slabs at service loads and then fluxural capacities of the slabs, right. So this is a step. So basically we are actually doing structural analysis, and typically moment distribution method is used for finding out the distribution of the moment. Then once you found the distribution of the moment, then checking for the stresses or checking whether the capacity is adequate or not, these are all basically very straightforward, which you have discussed it in the previous modules.